This is Mick Elliott of Electronic Specifier at European Microwave Week. I am on the Smiths Interconnect stand with William Wilson, RF microwave engineer. And William, perhaps if you could give us a little bit of background on Smiths Interconnect, about the company and where it manufactures.
Thanks, Mick. So Smiths Interconnect has a great heritage of high-rel products and developing components for space and defence. We have a number of facilities across the globe, namely in Dundee, serving the European market, and then we've got our manufacturing site in Costa Rica and our design team in Montreal and in Stuart.
Okay. And are specific products made in specific facilities, or does each facility pretty much fulfill the whole product line?
Yeah, that's a great question. So we split it up. So we've got our design and manufacture facility in Dundee that makes our waveguides, circulators, isolators, and some passive components for space and defence. We then have in Stuart, we have our design facility that make our board level components and our cables, where you can see some of our kind of mini lock products coming out in our K2 TVA, and those are manufactured in Costa Rica. And then we've got our Montreal team that do the optical transceivers.
Okay, and is it just space and defence, or do you look after other more commercial applications?
Absolutely,
as well?
Yeah. We look after commercial, industrial, and medical industries as well. But we see most of our kind of expertise and our heritage in both defence and space.
Okay, and that's where the research has been going in over the years. More, there's more happening in satellite communications.
There is, the emergence of new space and the like, more movement into LEOs, and so we're seeing an uplift in the need for our components to be smaller, more high-rel components, high-rel screening, qualification testing, and serving that market.
Okay, that's terrific. Thank you very much.
Okay, thank you.
Hi, this is Mick Elliott at Electronic Specifier. We've moved across on the Smiths Interconnect stand into their little conference and demo room. And I'm here with Alan McNeill, who is Product Line Manager, and he's going to talk about UHF transmit and receive front end. Alan?
Thanks, Mick. Well, this is a device here. It looks pretty large, and it's large because it operates at a low frequency, UHF, and it comprises a circulator, so which is acting as a duplexer, and a transmit and receive filters. And this is an integrated assembly using our own components designed and manufactured in Dundee, Scotland. And it was prototyped, and this is the prototype for the coming generations of deep space exploration, specifically on manned exploration, on manned vehicles. So for example, this would be part of the emergency transmit receive system on moon rovers, for example, or Mars rovers. It could be either. And the idea is that when the explorers, if they're in trouble, and this is their backup radio, call me and get some help. That's what it's for. So it's designed to be mounted on the active side, so the transmit and receive amplifiers. That's produced by our customer in Italy. And together this would be qualified for the European Space Agency's coming missions, provided these can be afforded, because they are not cheap missions. We're talking multi-billion dollar, pound, euro moon missions. So it's large. It weighs about 3 pounds. It's not yet at the stage where we could mass relieve it, take out some of the mass, but that will be the next stage. At the moment, we are just trying to get it working, which we've done. The next stage is qualification, to make sure that it will withstand the rigors, dynamic rigors, temperature rigors, and the problems with RF power in space.
Okay. What sort of testing are you going to do there?
Good question. Well, we're very well equipped in the Dundee facility. We have everything on site, so we can do the shake and bake. The shake simulates the launch and the mechanical shock when the solar sails deploy for the transit to the planet that you're exploring. So it's got to withstand that. Then of course, when you're actually on the planet, the temperatures can go from extraordinarily low to extraordinarily high very, very quickly. Depends if it's in the sun or in the shade, so we can simulate that. We can also do the simulations of does it work in a vacuum. So when you're on the ground, here in this conference room, things will work one way. When you put them into a vacuum, you take away the air, they work a completely different way. So we've got chambers that we can evacuate down to the specific, so 10 to the minus 6 torr, which is essentially a hard vacuum, and we can apply RF power, because under vacuum conditions, RF power does really strange things. So we have to make sure that it works under the conditions that it will operate. So after qualification, so temperature, shake, bake, mechanical shock, and TVAC, we can say that this design is pretty well ready to go into production. Once in production, we will actually repeat those tests on a 100% basis, because this equipment, when it's used, is actually for the preservation of life. So it doesn't come with any higher higher demands than that. So yeah, that's what we'll do.
Okay. I mean, you mentioned working with the customer. So where this is all integrated at the Dundee site, yes?
This is produced in the Dundee site. The next stage is we would ship it to our customer. They would bolt it onto their transmitter receiver. Then, of course, there could be feedback from there. Oh, it's not quite what we wanted. It's not quite what we needed. It meets specification, but it's only when you start to join the parts together that you find out that we should have done something else. So there'll be another perhaps minor development phase, and then we go into the production phase. Typically, from start to finish, that would be anything from a year to 3 years, and it might be 12, 15 years until it's launched. So it doesn't happen overnight. So throughout the process of the pre-sale, the design, manufacture, and the post-sale, you're in constant contact with your customer. It's a long game.
Okay. I mean, looking at the application, you mentioned deep space. I mean, it is an area that lots of countries are trying to pursue. Is that going to drive the market for these products?
To be honest, it's not a huge market. When you look at these missions are multi-billion. And the planned mission, the Mars recovery mission, where we're going out to Mars, I say we, the world, is going to Mars. I think the last ticket price was $50 billion. So it's not something that any one country does. It tends to be a global effort. And of course, with the situation in the world right now, cooperation is difficult to achieve, but it is a global effort.
Okay, and I mean, there's things like the European Space Agency.
The European Space Agency is funding this indirectly through our customer. We don't deal directly with ESA, but we do actually get funding indirectly through our customer. And they funded part of it and we funded part of it. And the reason we did that was because, first of all, it's an opportunity to showcase the technology, showcase our capability back at the factory, and also it's a really cool mission. I won't be working by the time this goes and hopefully comes back, but I'll be watching the TV. Okay, wishing it well.
So was this designed and developed in Dundee as well?
Yeah. We've got two main components. One is the larger and the obvious mass of this device, and it kind of looks like a car engine block. And these are cavity filters. There's 2 individual filters there. Then this little device here is a circulator, and it acts to buffer both the transmit and receive filters, and also to interface with the antenna. It offers them a constant impedance, a constant load on the antenna. So it was all designed in-house. The only thing that we purchased were the little cables, and the little cables were purchased from another company.
Okay. And just without getting ahead of ourselves, moving forward, I guess there is a plan where you'd look to reduce the size and weight, just because that is important, I guess, in space.
As I said, it's a fair old lift. I know that because I carried it from the UK yesterday. Mass used to be a driving requirement in space, but as the cost of space launch has gone down with people like SpaceX, they've greatly reduced the cost of getting stuff into orbit. Once you're up there, the mass isn't as important. but of course you've got to drive that mass forward. It has a momentum. So for every, it used to be $50,000 per kilogram to launch into geostationary orbit. I think that's down to about $20,000 now, around about there. So very much cheaper. But every time we reduce mass, we reduce the momentum, which means if you're on your moon rover, whatever, you want to apply the brakes, you don't keep going forever. I mean, I'm exaggerating, of course, but mass is a huge issue.
I think one of the things you mentioned was that this, you can use voice and data.
Yeah. I mean, back in the old days when the radios were voice only, they were in a simplex system, so over and out, Roger, whatever. This is a full duplex system, and we can get duplexing on this and transmit and receive because we've got this ferrite circulator allowing that to happen. So these days, voice is obviously still important if you want to convey something quickly, but data from the rover to the base, telemetry data, temperature, astronaut, health, etc., whatever they're sending back would be come back through a data signal. Because it's UHF, there's not an enormous amount of bandwidth, but it's what they can afford.
So, final question, when do we think we'll see this on Mars or the Moon? Or?
Well, I don't know. You're probably talking about within a decade, but it's all driven by funding. The technology is more or less in place. All these things are being developed for the Moon or Mars, whatever we're going, but it's all about funding. These are not cheap missions.
Okay. But this is ready to go anyway.
We're
getting on with the testing.
It's already at a TRL level above that, which the customer wanted for their prototyping. So the TRL when you launched would be 8, 9 for a mission, maybe a little less if it was a low-cost mission. This isn't, of course, but this is already at probably a TRL 4 or 5. Meets the concept. It's elegant, you can see it looks beautiful, silver-plated, etc. So it's already probably close to being at the point that we can qualify, at which point we would say TRL 6, TRL 7, and then it's up to the customer to use it and launch it. So maybe within a decade, but fingers crossed.
Okay. Alan McNeill, thank you very much for giving us that insight into Smith's Interconnect contribution to deep space technology. Thank you.
Thanks, Mick.